Hi everyone. Wanted to give you a little bit of background that you need for biotransport about a few mathematical details. Should watch this this online video before you go on to the next one, which is on the substantive derivative. So we're going to talk about three things today: the partial derivative, the dot product, and the gradient operator. Let's start with the partial derivative. So you all know what a derivative is. If I have some function, say f of x, and I take d by dx of that, that tells me basically how quickly does f change as x changes. And we know that there's a geometric interpretation of that, which is a slope of the f versus x graph. Now, as you go on in your studies, you're going to find that there are more complicated functions. For example, suppose that I had a function that depended not just on x, but also on some other quantity, call it y. And of course, we can ask the question, how does f change with x? So that's related to df dx in the old standard derivative. But we can also ask the question, how does f change with y? And those quantities are called partial derivatives, because if both x and y are changing, then obviously f is going to be, the change in f is going to be the sum of the change due to x and the sum of the change due to y changing. And so what we do with the partial derivative it has the symbol shown like that. And we can define two partial derivatives in the case of this function. The partial derivative of f with respect to x. So this is partial of f with respect to x, and this is partial of f with respect to y. And if you want to see a little bit more of a specific example, let's just go through a couple here. Suppose I have that f is equal to sine x times sine y. Now the idea is that when we calculate partial f with respect to x, we are going to hold y constant. So we only want to know, how does f change if x changes? And so for purposes of computing this derivative, this sine y term here doesn't change. So really we just have to do df by dx of sine x. So we know that that's the cosine of x. And then that gets multiplied by sine y, because for purposes of forming this derivative, as I just said, sine y is effectively a constant. And similarly, df dy is equal to, well, now we're going to hold x constant, so sine x is a constant, and then we're going to take d by dy of sine y, which is just cosine of y. So the rule is you hold constant any variable that isn't in the basement where you're taking the derivative. So here, when we did that, we held y constant because we were changing x. Here we held x constant because we're changing y. And let me just give you one other quick example here. Suppose that I had f is equal to sine x plus sine y. Well, in this case, df dx is going to be what? I get a cos x term from that first part, but now remember that this sine y term here is constant effectively, right? When I do df dx, and so what's the derivative of a constant? It's just 0. So the the partial derivative is just cosine of x. Similarly, if I do df dy, then the sine x term is constant, so when I differentiate that with respect to y, it's 0, and I just get cosine of y. So the whole thing is just cos y. So that's how you do partial derivatives, so we can check that one off. Let's now talk about the dot product. That's a little bit easier. The partial derivative idea it's actually a bit challenging, I have to say. Let's talk now about dot product. So a dot product is something that takes two vectors, and I'm going to call them A and B, and gives me, or gives back, or returns a scalar. And how does that work? Well, remember, we can write these vectors in terms of their components. So in a Cartesian system, we have the x, the y, and the z components. And I'm sorry, I've made a mistake here. I apologize for this. So obviously the components of A are not by and bz, but they're ay and az. So I have ax, ay, az that make up A vector, and bx, by, bz that make up B vector. And, very simply, to take the dot product, I do ax times bx plus ay times by plus az times bc. And if you have a hard time remembering what that sort of rule is, here's an easy way to think about it. The first components of A and B multiply each other, the second components multiply each other, and the third components multiply each other, and then you add them all up. And I hope you all see that this is a scalar, right? I'm just taking numbers and multiplying them and adding them, and so that's how the dot product works. So we can check that guy off, dot product, and let's now go on to talk about the gradient operator, which, just change pen color here. So the gradient operator is the extension of the derivative. Oh my goodness, I was supposed to say derivative, sorry about that. Derivative to two or more dimensions. And it has the symbol nabla, which looks like an inverted triangle, like that. And if I want to take the gradient of a function f, which depends on x, y, z, then what I do is I take df dx, df dy, df dz, and they form a vector. So the df dx is the x component of the vector, the df dy is the y, and the df dz is the z component. So this is something that takes a scalar and gives me a vector. That's useful to remember. And from our discussion before, I hope you realize that this first term here, the df by dx term, is essentially telling you how quickly f changes as x changes. This tells you how quickly f changes with y and with z. And so you have a vector that gives you some idea about how f is changing with each of its dependent variables, namely x, y, and z. So that's more complicated than just a regular old derivative, but you kind of need to know about that when you have functions that take multiple arguments. And so that's the mathematical background about this stuff. If you're not sure about this, maybe listen to this one more time, and then you can go on to the substantive derivative topic. Thanks for listening.